And we use both 20 Hz and 220 Hz with the features of the AirTem system. And the use of the dual moment is of course fundamental, is basic, to get at the same time a good resolution for the shallow part and for the deeper part. So this is the forward response that is produced by this synthetic model. So if we use only the 220 Hz, we have a good resolution of the first line. The red lines show the actual model, 1D model, while with the blue line we draw the covenant model by using this simulation. So by using only one frequency, we have good resolution of the first layer, but not of the deeper. If we use the lower frequency, we have an opposite result. Good resolution of deeper target, but not for the shallow one. The solution is to use both the frequency, so to use a dual moment, so that to have a good resolution of the model. You see on the field is very important. We suggest, above all for this kind of system, because it's a very flexible system. You can decide the frequency, the time gates, and so on. So it's very important to verify on the field day by day the result in order to be prepared to change, for example, frequency or anything. So we usually provide the evaluation of noise, of bias, of by means of high altitude flights provided, of course, by AirTem. And we can also provide a first inversion of data day by day, so to plan in the best way possible the prospection. This is an example in Sicily, in Italy, in which the customer wanted to save money. So they start with a very wide spacing, 1 kilometer for each line. Consider that this area is about 30 by 60 kilometers. So they started with the 1 kilometer spacing. We inverted the data and we decide where locate 3 infill area in which fly with a narrow spacing, with 100 spacing. So it's very smart in order to save time and money. You can evaluate day by day the quality of the data, the residuals, number of gates, and so on. You can compare the data with borehole, so to have an appraisal of the result. And also of some issues related, for example, to cabling. This is an example of processing of data in Canada, in Ontario. This is in Ontario, and we have in this case this coupling effect. You can see this very conductive layer that is fictitious. It's not real. It is due to this rod. Okay. And in fact, when the helicopter approach the road, you have an uprising of this. It is not real. So what is the solution? If you have this data day by day, you can suggest to change the direction of flight. In this case, it's better to fly not by this direction, this parallel to the roads. I don't know where they decide to fly in this way. Maybe it's more easy for the pilot. I don't know. So in this case, we can suggest to fly in the orthogonal direction in order to minimize the coupling. So it's very important. For the processing, we have a workbench software, which is a workflow in which we process the data. This is an example of raw data and decoupled. So in this area, we have coupling due to infrastructure. So we remove the data. We have no data in this area until the noisy it means that we average the data, we filter the data in order to increase the signal. It's very important to invert the data, otherwise you could get wrong results. This is an example of raw data collected in Denmark, and you can see these conductive features. But it is due to power lines, so it's features. Also, this one is due to infrastructure, so it's very important to decouple the data and to cut off all the wrong data. And also the noise data. This is very important also. This is a slice at 180 meters. And also in this case, you can see that the power lines cause these resistive features. It is not resistive. This is an example of profile. This is the raw data without any processing that are very noisy. This is our final result with a more geological meaning